Okay, we have looked at the properties of your simple covalent substances. Now we will look at the giant covalent structure or the giant covalent molecule. Okay, so all the atoms in the substance with giant covalent structure are held tightly by strong covalent bonds to form a giant covalent molecule. The two most common giant covalent that we are going to look at within the syllabus is your diamond and your graphite. Okay, so look at this picture over here. This is the structure of your diamond. So each black dot over here is a carbon atom. Your carbon is under group 4. They have 4 valence electron. One carbon atom is bonded. This is carbon atom number 1. It is bonded to 1, 2, 3, 4. One carbon atom is bonded to another 4 carbon atom, for example, over here. Okay, so I'm just going to draw it in terms of dot and cross diagram. It will look like this. So this part over here, we still have the unpaired electrons, right? So these unpaired electrons will continue to bond with another carbon atom, example, with its 4 outer electron. So the whole structure can keep repeating itself to form this kind of structure, what we call the tetrahedral structure. Okay, each carbon atom is joined to 4 other atoms by strong covalent bond. Okay, all the lines that you see over here is the strong covalent bond. Okay, which is maybe this bond over here, this one over here. These are all strong covalent bonds where electrons are shared to obtain the noble gas configuration. Okay, so as a result of this strong covalent bond, they need large amount of energy to overcome these strong forces, so they are usually hard. So since they are hard, right, we use them to make gems, jewelry, we use them for drilling rocks, etc. Okay, so this structure over here is our diamond. Okay, diamond have this kind of arrangement. Okay, they are carbon atoms and their atoms are arranged this way. Okay, the next structure that we are going to see, which is also the carbon atom, is this structure over here. So this structure over here, again, each black ball that you see or each black circle is a carbon atom. But now my carbon atom, for example, one carbon atom over here is bonded to 1, 2, 3 other carbon atoms. So again, your carbon has 4 outer electrons, but only 3 is used for covalent bonding. So this last electron is not used for covalent bonding, and it is actually delocalized between the layer. Okay, so when it is delocalized between the layer, we say it has weak intermolecular forces of attraction. Okay, so this dots that you see, right, this dotted line that you see is the weak intermolecular forces of attraction due to the delocalized valence electron that is not used in forming covalent bonds. Okay, so when we describe this arrangement over here, right, we call it hexagonal layers. Okay, so what is it? One carbon atom is bonded to 3 other atoms, okay, by strong covalent bond, and then it is in hexagonal layers. Okay, the hexagons are held by weak van der Waals forces. Okay, these weak van der Waals forces or weak intermolecular forces of attraction is caused by the last valence electron that was not used in covalent bonding, and it is being delocalized between the layers. Okay, so because of this, and there is weak intermolecular forces between the layers, graphite, we use it as lubricant because it is slippery, right? And because of the attraction force that is weak, then it becomes slippery. The next example that we are going to look at is this picture over here looks almost similar to your diamond. Okay, so this arrangement, now we are talking about silicon atom. So if you remember your carbon and your silicon, they are all group 4. So they have 4 outer electrons. So your silicon will have the same arrangement, yeah? One silicon atom is connected to 1, 2, 3, 4. 4 other silicon atoms. Okay, this is my mistake. This is 4. Huh? Okay, in another example over here, we have the silicon dioxide. This is sand. Okay, the common sand that we see is your silicon dioxide. Okay, silicon has 4 outer electrons, it can form 4 bonds. Oxygen got 6 outer electrons, it can form 2 bonds to achieve noble gas configuration. Okay, so look at this. You have one silicon atom. This silicon is connected to 4 oxygen atom over here. Okay, but my one oxygen atom is only connected to two silicon atom. Okay, so this description we will describe it as each silicon atom is connected to 4 oxygen atom, while each oxygen atom is connected to 2 silicon atoms. Okay, and then they form a strong covalent network. Again, this structure we call it a tetrahedral structure. Okay, so sand and silicon is used to make quartz as well as used to make glass. Good to know.